Have you ever stopped and thought about this? How is it possible that a machine weighing over 500 tons doesn't just tip over in the first second, but lifts off with perfect precision and flies straight through the sky? Today, we're breaking down how rockets actually stay stable during liftoff, and I promise after this video you'll never look at a launch the same way again. To understand the scale, think about the SpaceX Falcon Heavy. Its fully fueled mass at liftoff is around 1,420 metric tons. That's roughly the weight of 200 adult elephants stacked vertically. And this thing doesn't just rise slowly, it accelerates upward while fighting wind, gravity, and chaos. By common sense, something that heavy sitting on a pillar of fire should tumble instantly. But physics says otherwise. At first, humans learned how to launch rockets using simple gunpowder tubes. But that wasn't true controlled flight. That was ballistic trajectory. In the early 20th century, pioneers like Konstantin Tsiolkovsky and Robert Goddard realized that liquid-fueled rockets could achieve far greater thrust and control. Goddard's 1926 launch proved something revolutionary. A liquid-fueled rocket could lift off and fly a controlled path. It stayed airborne for just 2.5 seconds and reached 41 feet. But it changed rocketry forever. After that, progress accelerated. World War II pushed rapid advances in propulsion and guidance systems. The German V-2 rocket became the first long-range ballistic missile, reaching altitudes over 50 miles. Metal structures replaced fragile frames. Designs became more powerful and more stable. In 1961, the Soviet Vostok rocket carried Yuri Gagarin into orbit. In 1969, the Saturn V launched Apollo 11 to the Moon. And decades later, SpaceX's Falcon 9 proved that even a rocket could land vertically after launch, balancing on its own engine thrust. But despite all the innovation, the core challenge never changed. Stability is always about active control, so how does all that metal actually stay upright during liftoff? The answer lies in understanding the fundamental forces and the inherent instability problem. Every rocket during ascent is governed by 4 forces. 1. Thrust, the upward push from the engines. 2. Gravity, pulling it downward. 3. Drag, air resistance slowing it. 4. Aerodynamic forces, pressure acting on the rocket's surface as it moves through the atmosphere. Think of it like trying to balance a broomstick on your fingertip. When the weight is above the pivot point, the system is unstable. Any tiny deviation from vertical grows exponentially unless you actively correct it. Rockets face the same problem. The center of mass is the point where all the rocket's weight is concentrated. For a tall rocket with heavy fuel tanks, this is typically somewhere in the lower third of the vehicle. The center of pressure is where aerodynamic forces act. It's determined by the rocket's shape and how air flows around it. For a streamlined rocket, the center of pressure sits higher up, closer to the nose. When the center of pressure is above the center of mass, the rocket is aerodynamically unstable. Any tilt creates a torque that amplifies the tilt further. It's like holding an umbrella upside down in the wind. The wind doesn't straighten it, it flips it. That's the fundamental problem engineers must solve. You've probably heard that rockets are just built stable, like arrows with fins. That explanation is incomplete. Stability exists because the rocket constantly fights for it. And where does that control actually come from? You've probably seen rocket engines swivel during launch. That's not for show. That's the primary mechanism that keeps the rocket stable. Rocket engines are mounted on gimbals, mechanical joints that allow the entire engine to pivot in multiple directions. Hydraulic or electromechanical actuators control these gimbals, tilting the engine thrust vector by a few degrees in any direction. When the engine tilts, the thrust vector tilts with it. And according to Newton's third law, if the rocket pushes exhaust gases at an angle, the exhaust pushes the rocket in the opposite direction. The angled thrust creates a lateral force component. Even a small gimbal deflection, say 5 degrees, generates enough lateral force to counteract destabilizing torques. But here's where it gets remarkable. The rocket doesn't wait until it starts tipping. It predicts and prevents the tilt before it becomes catastrophic. Onboard sensors, gyroscopes, and accelerometers measure the rocket's orientation and motion with extreme precision. These sensors detect angular velocity, linear acceleration, and deviation from the planned flight path. They sample data at rates exceeding 100 times per second. The flight computer processes this sensor data in real time. If the rocket begins to tilt even 0.2 degrees off course, the computer calculates the required correction. It commands the gimbal actuators to pivot. The the engines by a precise angle generating a restoring torque that counteracts the disturbance. The response happens in milliseconds. No human pilot could react fast enough. The correction loop runs continuously, adjusting thrust direction 50 to 100 times every second. Consider the thrust vector equation. You don't need to memorize the formula. One thing matters. Small changes in thrust angle produce large corrective forces because the thrust magnitude is enormous. A 1-degree deflection on a Falcon 9 engine producing 845 kilonewtons of thrust generates roughly 14.7 kilonewtons of lateral force. That's enough to swing a 550-ton rocket back on course. Bernoulli and Newton aren't competing explanations for lift. Gimbal and feedback loop aren't separate systems either. They're one continuous correction dance. The rocket is never truly stable. It's constantly being stabilized. But engines aren't the only control system fighting for stability. Rockets face external disturbances that no amount of thrust vectoring alone can fully handle. Wind shear is one of the biggest threats. As the rocket climbs through different atmospheric layers, wind speed and direction change rapidly. A sudden crosswind at 30,000 feet can exert asymmetric pressure on the rocket body, creating a destabilizing torque. The flight computer detects this through accelerometer spikes and commands immediate gimbal corrections. Fuel slosh is another dynamic problem. Liquid propellant inside the tank shifts and sloshes as the rocket maneuvers. This changes the mass distribution in real time, introducing unpredictable torques. Engineers install baffles inside fuel tanks, physical barriers that dampen sloshing motion and reduce its destabilizing effects. On modern rockets like the Falcon 9, grid fins provide additional aerodynamic control. These are lattice-like surfaces that deploy after the first stage separates. During descent, they steer the booster by changing airflow around the vehicle. For upper stages operating in near vacuum, reaction control system thresholds take over. These small cold gas or hypergolic jets fire in short bursts to adjust the vehicle's attitude when aerodynamic forces vanish. Staging events introduce their own chaos. When the first stage separates, there's a brief structural shock. The rocket experiences sudden mass loss, separation forces, and temporary asymmetry as explosive bolts detach stages. The flight computer anticipates this. It adjusts gimbal positions and temporarily reduces sensitivity to prevent overcorrection during the transition. There's a fundamental trade-off. More control systems mean more mass. More mass means less payload capacity. Engineers optimize by calculating the minimum control authority needed for the expected disturbance envelope. If wind shear probability increases, gimbal range must increase. If fuel depletes unevenly between tanks, asymmetric, thrust compensation must activate. And all of this happens while the rocket burns fuel at rates exceeding 2,000 kilograms per second. So how does an actual launch unfold? At T-10 seconds, the countdown reaches final engine start command. Igniters fire, fuel and oxidizer flood the combustion chambers, thrust builds rapidly as engines spool up to full power, but the rocket doesn't lift off yet. Hold down clamps secure it to the launch pad. Sensors verify that all engines have reached nominal thrust and stabilized. Only when thrust exceeds the rocket's total weight, and all systems confirm green status, do the clamps release. That's liftoff. In the first seconds, the rocket executes a programmed tilt, a slight intentional lean away from the launch tower. This isn't instability. It's a calculated maneuver to ensure the vehicle clears ground infrastructure safely. As the rocket accelerates upward, it enters the region of maximum dynamic pressure, known as max Q. This typically occurs 60 to 90 seconds into flight, when the combination of velocity and atmospheric density creates peak aerodynamic stress on the structure. Engines throttle down slightly during max Q to reduce stress, then throttle back up as the air thins. Control systems work hardest during this phase. Aerodynamic forces are at their maximum, amplifying any deviation from the flight path. Past max Q, the atmosphere thins rapidly. Aerodynamic forces decrease. Thrust vectoring remains the dominant control mechanism until staging. When the first stage separates, the second stage ignites. The vehicle is now lighter, faster, and operating in near vacuum. Stability challenges shift. There are no aerodynamic forces to worry about, but thrust vector control and RCS thrusters must maintain precise attitude for orbital insertion burns. Throughout the entire ascent, the onboard computer operates autonomously. There are no human stick inputs. Every correction, every throttle adjustment, every gimbal command is calculated and executed by algorithms refreshed 100 times per second. Every time you watch a massive rocket liftoff, it feels like it's defying gravity. But it's not breaking the laws of physics, it's using them. Thrust vectoring, feedback loops, sensor fusion, gimbal actuation, everything exists in a continuous balance maintained by relentless computation. To me, that's the real beauty of rocketry. Not magic, but exact orchestration of forces at millisecond precision. And now I'm curious. Have you ever wondered how rockets steer in the vacuum of space where there's no air to push against? I've already made a video about that,